Hello and welcome to the T-Flow channel. In this video, we solve a classical laminar flow problem between two parallel plates using ANSYS Fluent. This is a well-known problem, which allows us to validate our CFD results. We consider steady, incompressible laminar flow of a Newtonian fluid between two infinite parallel plates, separated by a distance of h. The flow is driven by a uniform velocity imposed at the inlet. The distance between the plates is 0.02 meters. The working fluid is air, with a density of 1.225 kilograms per cubic meter and a dynamic viscosity of 1.789 times 10 to the power of minus 5 Pascal seconds. And the velocity of 0.05 meter per second is prescribed at the channel entrance. Before we start, make sure to subscribe to the channel and like the video if you want to see more tutorials like this one. We start by opening Fluent from the left panel. We click on the Geometry group and set the analysis type to 2D to avoid potential issues later in the simulation. From the Geometry section, we enter Design Modeler. We select the sketching plane and draw a rectangle. This rectangle represents the two parallel plates and the fluid region between them. From the Dimensions section, we assign the geometrical dimensions to our model. The length of the plates is 0.2 meters, and the distance between the two plates is 0.02 meters. Next, we convert the sketch into a surface. From the Concept menu, we select Surface from Sketches. We select the sketch and click Apply. Now, we generate the geometry. At this point, the geometry creation process is complete. Now we move on to mesh generation. Due to the simplicity of the geometry, we can use the default Fluent mesh with a smaller element size. Alternatively, we can create a more refined mesh. To generate a more accurate mesh, we need finer cells near the walls, where velocity gradients are stronger. We select the two wall edges and change the method to number of divisions. We set this value to 50 and adjust the bias type as shown in the video. Using face meshing, we generate a structured mesh. Although further mesh refinement is possible, it is not necessary for this analysis. Next, we define the inlet and outlet boundaries. We select this edge and click on Create Name Selection, then rename it as Inlet. We repeat the same process for the opposite edge and name it Outlet. After that, we update the mesh and move to the Setup section. We enable double precision and start Fluent. The only physical model we activate is the laminar viscous model, since the Reynolds number is within the laminar flow regime. There is no need to modify the material properties, as air is already defined by default. In the Boundary Conditions section, we select the inlet and specify the inlet velocity. For this problem, the inlet velocity is set to 0.05 meters per second. For the solution method, we use the coupled scheme, although simple-based methods can also be used for this case. We then configure the residual monitors. The solution is initialized using the hybrid initialization method. Finally, we start the simulation with 200 iterations. Due to the simplicity of the problem, the solution converges very quickly. To visualize the velocity profile, we create a line on the lower plate as shown in the video. And from the XY plot menu, we generate a plot using these settings. To examine the velocity contours, we can either use Fluent directly or post-process the results in CFD Post. In CFD Post, we create a contour plot, select the appropriate location, set the variable to velocity magnitude, and choose 50 contour levels. As we can see, the flow between the two parallel plates is fully developed, and the velocity profile exhibits the expected parabolic shape, which is consistent with the analytical solution for laminar Poiseuille flow. Thanks for watching. If you enjoyed this tutorial, don't forget to subscribe and like the video. For more tutorials, stay tuned, and if you have any specific problems or suggestions, write them in the comments below. We'd love to hear from you.